Okay, so we can get started. So our next speaker is Thomas Kipf. Thank you so much for coming to give a talk. So
Thank you for the invitation.
Thomas is a research scientist at Google Research in the brain team in Amsterdam. And prior to joining Google, he completed his PhD at University of Amsterdam under Professor Max Welling on the topic of deep learning with graph structure representations. And his research interest is in the area of relational learning and in developing models that can reason about the world in terms of structural abstractions such as objects or events. So now over to you, Thomas.
Yeah, thanks so much for the kind introduction and for inviting me to speak here. I'm super excited to be here, especially in this lineup of speakers you already had this week. Yeah, my talk is going to be about relational structure discovery. So as you've heard, my PhD was about deep learning with graph structure representation. And I'm mainly interested in how can we essentially enrich deep learning architectures with structure representation, such as in the form of a graph. And very often we're not given the graph at hand that we want to learn on, but we kind of have to infer graph structure description from our data. And this is going to be the topic of my talk today. And this spans research both over my PhD and more recent work at Google Research in the brain team. Now, by relational structure, what do I actually mean? So you've heard a lot about graphs and networks in previous talks. But what I want to highlight here is that essentially graphs or networks are about representing the world's information in terms of entities and their relationships. And we often don't think too much about what does this representation actually buy us, but it's a very powerful abstraction. So we have essentially that it's very easy for humans to interpret. We can very easily kind of read off. We think about the world ourselves in terms of objects and relations. We perceive the visual environment in terms of objects. We communicate in language about objects and their relations. So this is a very kind of natural abstraction for us. At the same time, this abstraction is almost nearly universally applicable. Entities and relations can be pretty much anything. And as you've seen, if you work in this area, graphs just also come up everywhere. You can work on traffic modeling problems, but you can also work on physics problems and the World Wide Web and social networks and so forth. And at the same time, it also allows us to combine information in near infinite ways and in sensible ways. Because you have these composable building blocks of entities and relations, you can compose them in many ways, and the outcome is often sensible, and that just buys you a lot of expressive power. And it comes to no surprise that graph structure data in the wild is very prevalent. You have social networks, citation networks. You can also represent maps and road networks effectively as entities and relations, road segments between intersections and so forth. But also communication networks, the World Wide Web, knowledge graphs where you have typed relationships that have certain relation types and directional relations like citizen of, educated at, and so forth. But you can also represent dynamical interacting systems, physical systems, biological systems, like protein interaction networks, and so much more in the form of a graph. And it also comes to no surprise to you that graph neural networks have been, in the recent years, really became an established method for learning with this type of data. And this is especially remarkable because when I started my PhD a bit over 5 years ago, there were maybe a handful of papers on this topic. And at that time, people didn't really think about using neural networks for this type of structured data. But now you have thousands of papers, and it's a huge community, and it's very exciting to have also witnessed that growing. And so graph neural networks are established methods for compositional reasoning tasks, more classically things like node, edge, and graph classification, of course. That's where most of these methods came from. But also for things like physics modeling, you have the same technique and the same kind of representations that buy you a lot of generalization power. And just one thing I want to highlight here is that the typical assumption for many of these applications where we use graph neural networks are that we know what the entities and what the relations are. maybe not so often the relations, but most of the time we really assume, okay, we know what the nodes, what the entities are. And that's kind of the core assumption for deploying graph neural networks. Now, in my talk, I want to basically ask two questions that relate around like loosening this assumption. So what if, on the one hand, we have incomplete knowledge about relations? And that leads us to things like latent graph learning or link prediction, graph completion, recommendation, these kinds of problems. But also models that kind of learn to infer relationships, like rich descriptions of relations from scratch, such as like works on neural relational inference. And the second part I want to touch upon is like, what if we don't even know what the nodes and the entities are? And this is very important if you want to work with natural data, like images, video, or any kind of perceptual data that an agent might perceive in the real world. They might want to reason in terms of like objects and entities and relations as abstractions, but they don't have access to them just based on their sensory inputs. And so it's a very important topic to kind of try to infer like what are good structured abstractions in the first place. And this leads to areas such as object discovery, entity discovery. And it often boils down to grouping or clustering of lower level features, which I want to talk about today. So I'll start by diving into some pretty quick introduction into graph neural networks. I'm sure you've already heard more than enough about that this week, but I'll keep it short, just for anyone who watches, just drops into a live stream. And I want to then briefly touch upon graph neural network-based link prediction, but also more general models on inferring relationships from scratch. And then I want to focus on attentive grouping using an architecture called slot attention that allows us to infer entities from scratch from raw perceptual data. And then I want to quickly dive into how we can put that all together into an architecture or type of model that's sometimes called a structured world model, where essentially try to both infer relationships, causes, and entities and objects from scratch and model environments that way. So the bigger picture for graph neural networks, as already back in the days with like the graph neural network model and some earlier papers, is essentially you pass messages along the edges of the graph, which are parameterized by neural networks. You agglomerate those messages and you transform them, and you keep on repeating that, and maybe have some nonlinear activation functions in between or nonlinear transformation functions. And just for the purposes of this talk, I'm going to denote node features usually by HI and edge features by HIJ. And I think the most prevalent formulation these days for graph neural networks is probably the neural message passing framework, also used in like the GraphNets formulation. And here, like the main abstraction is, okay, you have these message functions and edge update functions, and they are just learnable functions that take into account pairs of node representations. And usually you would restrict those message functions to nodes that are connected in the graph by an edge. And then these edge update functions could, for example, be an MLP or some linear function. And then you would iterate by passing these messages. So you would calculate these message functions and then run node update functions. And here these node update functions are usually also MLPs or some kind of abstract node function that take into account both the agglomerated messages using a sum or some other agglomeration operation, maybe some additional node features, and the previous representation of that node. And just for completeness, there's of course many flavors of this and like a myriad of architectures these days that fit into this description, starting from like convolution-based graph neural networks that essentially just use linear message functions, where you would also have like a weighing factor here, alpha ij, for each edge that is typically defined by the graph structure itself. Then you have relational models typically used for knowledge graphs, where you enrich that description by having separate message function for each edge type. But also, ultimately, the most popular architectures these days are probably self-attention based, where the main difference to the architectures before is that you learn this aggregation weight as a function of your neighboring features using some softmax attention mechanism. And of course, the exact implementations vary. This is just an example here. But I think the interesting bit is like how flexible this framework is. Like you can take any kind of graph data set, and usually we know, okay, we can put a node classification module on top of each node representation that we learn. We can agglomerate these representations. We can do graph classification. But we can also use this for kind of inferring missing information in graphs in the form of missing links. And so here, the simple recipe that you've probably seen quite often is you just encode your graph by running message passing operations. And then the idea is simply to query those message representations at the end with a decoder that just takes into account two neighboring node representations or two node representations that you would like to ask, okay, are these connected or not? And then you have like a scoring function or a function that gives you a probability that these two nodes are connected. And in practice, we would train this with a contrastive loss. So here we would train by taking some positive examples. But since we cannot typically just enumerate all the negative examples in the graph because there's n square many, we sample some negatives to train this efficiently. Now, the interesting bit, however, I think is when we can ask the question, okay, what if you're only given nodes and we want to infer relations from scratch? So let's say we're given some kind of mystery physical system where someone highlights us all the individual atoms and gives us all the properties of these atoms or particles, but we don't know anything about how they interact, if there's maybe some underlying interaction graph. And we would like to infer kind of the meaning of the relations, like what is the effect of a message function, essentially, like a force in a physical system, but also if there's any kind of structure in the interactions, like are certain nodes kind of only connected to certain other nodes, for example. And here the observed dynamics could be any kind of dynamic system that is composed of kind of multiple particles. So you can think of like sports games, multi-agent systems, but also simple kind of particle physics kind of situations as applicable here. And the simple recipe for this kind of model is essentially you observe the dynamics. So someone gives you the representation of your system in the form of a number of nodes. And for each node, you have like observations at different time steps, like from time step 1 to time step capital T. And this would tell you something about the dynamics of the system for a given snapshot. And then the idea is now, since you don't have any information about how these nodes might interact or what kind of relational structure dictates the dynamics of the system, all you can do here is you either assume a fully connected graph or maybe some kind of nearest neighbor graph on which you would like to exchange information in the system. So what we do here is we use a graph neural network applied to the fully connected graph. So basically, we pass messages along all the edges between all possible pairs. And then this graph neural network is tasked to predict or to make a proposal for how these nodes should actually interact. So the graph neural network says, for example, okay, here the violet node and the green node are likely to interact. Whereas given how the dynamics look like that we've observed, the red node and the violet node are likely to not interact. And this is still an unsupervised model. So essentially, the model just makes a proposal, which takes the form of a posterior distribution here. And since we kind of want a discrete graph, we want to really understand in a human understandable way, like what are the actual structures that dictate the dynamics. We assume we have a discrete graph here, and we use a Gumbel softmax trick for training. So the whole architecture takes the form of a variational autoencoder. And we can train this because we take a soft relaxation of the kind of discrete graph, and then we can backpropagate through the whole system. So what happens now if we have like this interaction graph proposal? We can then run another graph neural network that is only allowed to pass messages on the edges that were predicted by the encoder. And in that way, the model kind of has to make a hypothesis for how things are connected. And then given its hypothesis, then it's either easy for it to make a prediction for the next time step, because maybe then it's easier to learn the physical dynamics. But if it has proposed an unrealistic graph, then it would be very hard for it to predict the future dynamics or reconstruct the dynamics. And so that's the overall idea. And the model is basically only trained with two simple loss components. One is a reconstruction component, and one is a regularizer that you can control whether we want to have a sparse graph or a dense graph, for example. And what we already know from like graph neural networks and physical systems is that this kind of simple architecture allows us to accurately model and predict physical dynamics well into the future. So given some kind of initial observation of some physical systems, like some particle dynamics that are connected by springs or by Coulomb forces, like charged particles, then we can predict the future dynamics quite accurately. But the interesting bit is that this simple inductive bias allows us to also discover the ground truth interaction graphs. So what has happened here in these environments is that we instantiate randomly sampled graphs for all the training examples, and this generates some dynamics. And so the model essentially at new unseen kind of simulations at test time, it can infer these hidden graphs without having ever been supervised to do so. And this works both for very simple dynamics with these springs, where you have linear interactions. In the charged particle system, you have inverse square law interactions. So these get much weaker the further apart the particles are. That's why it's slightly harder for the model to learn these interactions. But then you also have like highly nonlinear interactions, like in this Kuromoto system, which are oscillators that are coupled by their phase. And here, the strength is not dependent really on like vicinity or anything, but is a complex nonlinear interaction. And in this case, also the model is able to uncover the latent graph. So this has since been also extended. There have been many extensions, for example, also on extending this work to apply to environments where you have changing graphs or dynamic graphs over time. But I just want to highlight two extensions here, which I find quite interesting. One is that you can actually connect this type of graph discovery mechanism to causal discovery. So you have kind of for a very specific type of causality, which is called nonlinear Granger causality. So that's basically if a dynamic system and you would like to discover the Granger causal links, whether one kind of trajectory influences another trajectory over time. And similarly, this has also been extended for discovering other kinds of structures. Like so far, we could only control the sparsity of the interaction graph that we want to discover, but it can also put on further constraints, like for example, only discover latent spanning trees. And this can be done with a technique called stochastic softmax tricks in a paper by Paulus and Joy and others. And I just want to mention that this whole area of latent graph learning is of course much bigger than what I presented here, and there have been many works before, like the rise of deep learning in this space, in classical network interaction, inference, where people try to infer interactions of nonlinear dynamic systems, like in this paper by Casadego and others. But also in the graph signal processing community, these things have been analyzed, and there's a nice review paper by Dong and others from 2018 here. But in recent years, this has really become an emergent areas for graph neural networks and beyond. Like there's also work such as this differentiable graph module for GCNs, and also a really nice blog post by Michael Bronstein, who gave a talk already on latent graph neural networks. And lastly, transformers are like all the rage these days. And we, of course, also know that transformers are effectively learning some kind of latent graph description. And especially, this has also been investigated already in 2018 on how can we learn like multi-relational graphs using transformers for like textual understanding, and how can we transfer those discovered graphs to other problems. And of course, any other sparse attention mechanism can be kind of cast in the same kind of latent graph learning picture. So now having talked about like relation discovery, I want to focus on the second part of my talk, on what can we do if we don't even know about the entities in a system. So we still want to use effectively like graph neural networks and all the symmetries or like the generalization properties they allow us. But then on more naturalistic data where we might not even have access to like meaningful nodes in the system. And here I want to highlight one work from last year in Europe that essentially performs some form of attentive grouping of lower level features, which we call slot attention. And so this work effectively performs a competitive attention mechanism that runs on top of some kind of visual representation. Let's say you get an image, you encode it with a CNN, you get some kind of grid representation of the image, but the grid nodes themselves don't give you a good kind of abstract representation that would be useful in a graph neural network. So what we instead want is we want that each object is really encapsulated in one slot or in one node of our abstraction. And to get there, we have this slot attention module that performs this iterative competitive attention mechanism and effectively learns to route information or group information from the lower level features like the visual features into like abstract slot representations that you can then use like nodes in a graph, and then you can use like graph neural networks on top for reasoning problems. And so this is joint work with an intern, Francesco Locatella, from last year, and many collaborators at Google Research. And we look at two different architectures here. So on the one hand, this can be done completely unsupervised in an object discovery architecture where we simply put this module on top of an encoder and then place a decoder after the module and try to reconstruct the original image. And what's important here is that each slot that we infer gets reconstructed individually back into the image, and then we recombine the image at the end. But we can also use this directly to do kind of reasoning in the abstract space. So we map from the image to some kind of abstract set representation, and then we can try to predict set properties from there. For example, object properties or the allocation in an image. Now, just to highlight the core prediction problem that we're looking at is it's essentially to learn a mapping from an image or some kind of other modality to a set of variables. And intuitively here, each set element should capture, for example, an object, a part, or a background. Typically we have like a feature grid, like for images, and then we would like to aggregate them into the slot representation. And if you're familiar with capsule nets, then this is a very similar idea. So capsule nets essentially do the same thing with one crucial difference. So in capsule nets, you assume that the slots have no symmetry. So basically, there's always a slot number 1, which might specialize to only capturing houses. There's a slot number 2, which might, or capsule number 2, which might always specialize to capture dogs. And so you have like these specialized class-specific capsules in capsule nets. And so the difference here is that these slot representations are effectively universal slots that can capture any kind of representation in the input, irrespective of their order. So slot 1 could capture a dog, slot 2 could also capture a dog, but a different dog in the image. But then in a different instance, slot 1 could capture a house and so forth. So there's no particular ordering, and this set symmetry, this exchangeability, buys us a lot of generalization power. And the way we instantiate this module is effectively by a simple kind of clustering algorithm that is learnable. So we start from sampling slot representations from just a Gaussian distribution for which we have like a mean and a standard deviation that we predefine or learn. And then for a number of time steps, so it's an iterative module that we apply maybe up to 3 time steps. We perform an attention mechanism that is just a dot product attention between inputs and the slot representations that we have from the last time steps, with some learnable projections like key and query projections here, which are linear matrices. And then we have a simple softmax attention mechanism that, different from regular kind of transformer style attention, is now normalized over the outputs of the attention mechanism, like over the slots here. And what this does is that it induces competition or communication between the slots. So that means that no one object can be simultaneously in 2 slots. And we aggregate these updates using a weighted mean. Regular attention would use a weighted sum, but we use a weighted mean here so that it's all nicely normalized, because we haven't normalized yet over the input of the attention mechanism. And lastly, we pass this through like a recurrent unit to make it more effective at gradient-based optimization. And so the interesting thing here is that if you compare this to regular clustering, and I'm highlighting here soft k-means, which is like a soft version of the k-means algorithm, then this is quite similar. And effectively, in soft k-means, what you would do, you would have the same kind of initialization, but instead of using a dot product in a high dimensional abstract space, you would use simply Euclidean distance of your cluster centers, the slots, and the inputs. You would also have a softmax that kind of gives you these weights. You would aggregate with a weighted mean, but then instead of having a learnable recurrent update, you would just write these updates into the slots again, which of course makes optimization harder if you have multiple time steps. And the interesting thing here is that slots have to now compete for explaining the input, which we can nicely see from this clustering algorithm analogy. And so the overall architecture, as already mentioned, for object discovery is essentially you take some kind of image backbone, like a CNN, you put this module on top, it gives you abstract object representations, and then you can decode each individual slot back into the image. And each slot decodes an image and kind of an alpha map, like a map that tells you how likely is each pixel to be reconstructed in the final image, so that you can then recombine all these images into one single image. So it's like you have RGB and an alpha channel for each slot. And what we see is if you just apply this in some standard benchmark in this space, like this Clever data set or these multi-D sprites and Tetris data sets, is that apart from the background, which kind of gets washed out over all the slots because there's no particular symmetry to the background, all the individual objects are nicely decomposed, and each slot really captures one object and can reconstruct only the object that it captures in the environment. And that, of course, makes it much easier if you then want to use some kind of graph neural network on top to perform some kind of reasoning task, because now all the information of that object is captured in that slot. And what we also find is that we can also generalize in a number of ways with this model. So on the one hand, we can, because the recurrent inference module, we can use more iterations at test time. So we trained this with 3 iterations, but we can use up to 7 iterations at test time, and the kind of decomposition and segmentation performance that we get from the model increases, while of course being more expensive to run. And here the segmentation performance is measured in the so-called ARI score, and that's a measure to measure clustering similarity, which effectively measures like the quality of the segmentation. And what we also see is that we can generalize to more objects at test time. Like here, we train it on Clever 6 with a data set with 6 objects at maximum, and then we can test on images with up to 10 objects, and the model can still very nicely decompose those scenes. And we can highlight or visualize 2 different kind of things in the model. On the one hand, we have these attention coefficients in the encoder of slot attention that tell you where the model kind of gets information from the image. And then we have these reconstruction masks that the model uses to recombine the final image for reconstruction. And what we see in both cases is that in the first iteration, things are still mixed and objects are not perfectly decomposed. But in later iterations, the decomposition is almost perfect. And the model learns to separate these objects into individual slots and give you a kind of a crisp reconstruction of each object. Now, what you've seen previously is that the model typically puts like the background into like spreads it out over different slots. Since there's no particular inductive bias in the model to either split up the background or put the background maybe into one particular slot, we sometimes also see runs for certain random seeds where the model actually puts the background into a separate slot, which kind of looks cleaner, which is an example I'm highlighting here. And here it's nice to see that this is a model trained with 11 slots that we train on scenes containing up to 6 objects. And what you can nicely see is that the model can even keep like slots completely empty. So as long as we specify kind of enough slots for training, the model can kind of assign like empty slots that don't really carry any information about the scene. And if you would use then a graph neural network for downstream tasks on top of that, usually the graph neural network would also be able to handle kind of these empty nodes. And now for generalization, what we see is if we train this model on just 6 objects, you can also nicely see here with scenes that are much more crowded, the model can still kind of learn to generalize because it has kind of learned a general decomposition algorithm, and it can separate those scenes even into more objects. And we can even vary the number of slots we have in the model during training and test time. So one part I also want to highlight is how we can use that module if you don't want to use it in an autoencoder, but maybe for some downstream task in the abstract space that you learn. And in this setting, which you can view as a set prediction setup, the architecture is quite similar. You start with a CNN backbone, you put your module on top, and then you can further have like a graph neural network or some kind of model that refines the prediction of the set representation that you get. In this case, we use an MLP with shared parameters that is independently applied on each node or slot. And to train this, we can use a matching algorithm because we predict a set in random order, that it doesn't have any specific order, and the order also doesn't mean anything. And the ground truth labels might also be some kind of set of nodes that are labeled. And so in order to align the two, we have to use a matching algorithm, for example, Hungarian matching. And what's important to note here is that this kind of setup has, in the meantime, also become like one of the predominant setups in which like detection setups or segmentation is done in computer vision. Starting with this concurrent work on detection transformers, DETR, which is mentioned down here, the idea is very similar. You effectively start from an image, and then you have like an image to set module. And many computer vision tasks can be represented that way, that effectively the output space is very often set. So this is kind of a very powerful paradigm for treating many of these set prediction problems. And what we see here is that in the case of the supervised prediction, let's say we only want to predict certain object properties like shape and color, then the model still learns to attend to the right object at training time. And even though it's not directly supervised to do so, so these object masks, which are not supervised, they emerge during training, and they highlight the individual objects. Now here it's a bit more noisy because this is all done in kind of not an image space, but already in the learned representation space. And it's also competitive to some earlier baselines. And I think it's especially important to highlight the yellow baseline here, the slot MLP. This is a baseline that predicts an ordered representation. So it doesn't do set prediction, but it predicts just all the nodes at once. And this performs very poorly in terms of generalization. Now what you see here is if we run this model for a couple of iterations, in the first iteration, predictions still pretty messy, but then as I go along, the predictions get refined and the model learns to focus on the right objects, which again shows you that it's kind of, you need this iterative disambiguation mechanism to really break the symmetries in the system here. Now, since we released this work, there have been a number of follow-up works on slot attention. On the one hand, so what we've shown here is only on very simple kind of toy benchmarks where we have, for example, this clever data set on simple gray backgrounds and colored objects. So it's not very difficult to segment those. But it turns out you can also segment like real world complicated video with complex textures if you, instead of taking the RGB values of the scene, you take optical flow as kind of your grouping signal. And then if you run an optical flow image through slot attention, you get similar kind of decompositions even for real world videos. And another interesting paper is this Right for the Right concept, where the authors show that you can combine the representations learned by slot attention with a symbolic reasoning module. This is possible because the representations are nicely decomposed, and then you can really nicely interface this with also classical symbolic annotations. So before I conclude, I would like to just give a brief overview of how you can use these kind of structured representations directly from raw visual inputs to reason about environments in a dynamic fashion. And these kind of structured world models, they typically follow some kind of slot-based object-centric architecture, like what I mentioned before. You have like an image as a basis, or you might even have an audio wave. And the core part of these methods is, again, you learn an abstraction from this grid representation to a set representation, where now you have a number of slots that represent important parts of the input. And if you now want to do like dynamics modeling, you can effectively have like a reasoning component or like a graph-based module on top that learns the interactions between those nodes over time. And you can then have any kind of downstream task or loss that you use to train the system. And the important part here is that all the everything that happens as soon as you move away from the grid is symmetric under permutation. And so this permutation symmetry, so that basically means the reasoning module that you put on top of is equivariant under permutation. And what this buys you is a lot of generalization power to different. So the model is no longer sensitive to in what order you represent the nodes, but you can also very easily generalize to adding more nodes at test time or reason with new combinations of things. And in this paper on contrastive learning of structured world models, we essentially look at one of these pipelines where you start from an image, you extract the objects, in this case with a very simple CNN module because that was before slot attention, and you encode these into a set of slots. In this case, these are ordered, but this is sufficient for the environments we look here. And then you use a graph neural network as a transition model to predict the next time step. And the interesting part here is that we use a contrastive loss directly in the latent space so that no decoding is necessary to train these models. So the encoder here, as I mentioned before, is just a simple CNN, and we use simply each feature map as the basis for one object slot. And this only works for environments where you have like a fixed number of objects of a fixed types of colors. So as long as you have one yellow object, one blue object, then the model can always put the yellow object in the first slot, the blue object in the second slot, and so forth. Now, for more complicated environments, you would need something like slot attention. And also the transition model, something very simple suffices here. So we can essentially just use a message passing neural network where the edge function just takes the representations that we learned from two nodes as input, and then the node update function also takes an action that an agent might execute on the environment as input, and then predict the offset for the next time step in the latent space. So the model predicts these updated object representations, and so effectively this delta ZT, and we get the final representation by adding those two. It's like a skip connection in this case. Now, for training, the important part here is the contrastive loss. So typically, when we want to train these models by auto-encoding in pixel space, if you have very complicated textures in the pixel space, then this becomes very difficult for training these models. So you've seen in the past section that some people now use optical flow to circumvent this issue. But you can also circumvent this issue by just putting a loss directly in latent space. And this also avoids modeling of task-irrelevant details like colors or backgrounds that you might not be interested in for the particular task that you want to solve. And the loss we use here is relatively simple. It's a hinge loss, so it's not like a classic info NCE loss that you might know with softmax, kind of over inner products of features. But what we do here is we simply calculate the positive energy of a state action next state tuple. So we encode one object in its latent state. We add the output of the transition model to it, and we compare this final representation to the case where we would directly encode the next state with the same architecture. And these should, of course, be close. So it's kind of a transformation equivariant loss function that we apply here, or trans-E loss that was also used in graph representation learning before. And we can contrast this against the energy of a negative example, for which we just use a tuple of a state and a random other state, maybe from some different episode or from the same episode. And what we see, so we apply this to a couple of environments, like multi-object environments where an agent can move individual objects, Atari games, and also a gravitational physics simulation where there are no actions. So you have either actions that individually control objects, you have global actions in these Atari games where an action can affect multiple things, and then you have this three-body physics simulation where we have no actions. And we get experience, or we get data for these environments by just running a random agent on those for simplicity. What we find is that with this simple architecture and this latent space loss, again, we see that a model can learn object-specific abstractions from these environments. Like here in these cases, every feature map would highlight or would be sensitive to one particular object and then encode the properties of this object in the latent space. And if we inspect the learned latent space, what's interesting is that it really captures all the transition dynamics and the symmetries of the underlying system. So basically, if you look at the left plot here, there we have the system where an agent can move individual objects. And if a certain location is already blocked by an object and you execute an action, like if you want to move the yellow object to the left, then nothing happens because the blue object is already there. And all of these dynamics are reflected in the latent space that the model learns. So let's say we only now, after training, let the agent control the yellow object. Then what we see is that where the other objects are in its latent space, the model predicts that if an action would happen from a certain location adjacent to these objects, it would not predict a transition happening into that particular position. So nodes here are particular states that get encoded into its latent space, and edges are transitions that happen when you execute an action. And so the model really understands that certain actions are possible and certain actions are impossible in the latent space. And we see the same happening for the other environment. So to summarize, I would like to just go back to the relation discovery part and summarize by essentially reminding you that the graph neural network inductive bias is not only useful for learning with graph structured data, but also for discovering relational structure. So you can use it as a bottleneck, or essentially as kind of an algorithmic, bottleneck or structure that aligns with the task at hand, and therefore the model has to get the information flow through this kind of algorithmic bottleneck to solve the task. And by that, it can discover these latent graphs. And similarly, if you want to use it for entity or object discovery, you can find entity or symbol-like abstractions from this environment, but only for relatively simplistic environments. And doing this in an automated and task-adaptive manner for much more complicated environments and in a much more general sense is still a major open challenge in machine learning. But I think that these differentiable and attention-based interfaces that I've shown here are at least a promising direction to follow for this particular goal. Now, just want to mention what I think are important future research directions in this area. So on the one hand, for structure discovery, like discovering entities and relations, I think we still have to look at other domains like text, speech, and video, like other natural domains where these types of abstractions might be useful, but also exploring other learning paradigms. So I mentioned things like autoencoding or contrastive learning here, but you could also imagine other latent space losses or downstream tasks like reinforcement learning. And lastly, combining the structure discovery part together with reasoning and prediction tasks so that a model has to learn the optimal graph structure in terms of both entities and relations to solve a particular downstream task. And for this, I think we also still need many benchmarks because they're crucial for measuring progress, and the field is still pretty young. So with that, I would like to thank also my collaborators, both for slot attention and Google Research, but also earlier collaborators at the University of Amsterdam, Free University of Amsterdam, and University of Toronto. And I think we have still a few minutes for questions. Thanks.
Yes, we do. Thanks. So now we can thank our speaker. So we have a few questions on Slack. So I'll just read them. So the first one says, how do you encode the temporal dimension for the graph in the neural relational inference? Are they node features? Do you model trajectories somehow?
That's a really great question. And so the answer is that we tried a couple of different things. So the default setup we have is we just concatenate the features over time. So let's say we have 3 time steps, and for every node we have a feature at every time step. So then for every node we concatenate those features along the time dimension. And then we just feed it through an MLP. That's the simplest architecture. What we found to work better is to use a CNN or some kind of recurrent model that encodes the time dimension. And then we have an attentive pooling operator that pools the encoded time dimension, the encoded time representation into a single vector. And this helps us that the model can essentially focus on the important parts. Like in some interacting systems, you might only in rare cases have an interaction happening. And so the model needs to be able to kind of focus on that particular time where the interaction is happening. But all of this assumes like we only have like a small window of time steps that we condition on. And you can unroll the model on much longer sequences by basically treating this as kind of a window which you encode, and then you can use a rolling window approach to model the whole dynamics.
Mm-hmm. So in that case, is it successful at capturing those relations? Just because, for example, we are assuming that there's some sort of message passing kind of happening. So if there's an interaction, then the features would, in a way, like be passed onto the other nodes.
Yeah, so I think what's important is to abstract the past, which we use as a context for the relation prediction, into a single kind of node representation. And then it can, if some interaction happened during that time, it can encode that in that single node representation. And then this kind of relational bottleneck that we have can then use that information to predict, okay, which ones have actually been interacting. So if you wouldn't use that window, I think the model wouldn't be able to do that. But I'm not sure if that answered the question.
A little bit, yes. So thanks. We can. So that question was mine. So we can just go to our next question. So Mehdi asks, can you inject some prior knowledge about the hidden graph through a prior? For example, assuming instead of assuming a fully connected graph at the start, assume that it's a small world network.
Yeah, that's a great question. So there's two ways in which we can kind of restrict the graph. On the one hand, we can just hard restrict the graph to basically in the encoder part, we assume the fully connected graph, but already at that stage, you can kind of have a graph template on which you're allowed to do the kind of graph discovery. So this could already be a nearest neighbor graph to make it more efficient. And then only within that nearest neighbor graph, the model is still allowed to kind of predict relation types. Now, for small world properties or like more abstract properties of graphs, it gets a bit more complicated. So far, what the model can do with just a simple VAE formulation is you have control over the sparsity. Like that's the only parameter you can really choose in that kind of formulation. But if you wanted to have some kind of other structures like a certain latent spanning tree, that's something that's easy to control for. But if you wanted to have like a small world graph or like a preferential attachment kind of graph, then you would have to sort of model the I guess for preferential attachment, you would probably have to model the generation process of that graph and have like a different decoder mechanism. So I guess the way you could resolve this is instead of predicting every edge simultaneously in a pairwise fashion, you would kind of use a graph neural network to encode the states, and then you have like a sequential mechanism that would predict these edges, and that sequential mechanism then you can control to have certain properties for prior.
A follow-up on that maybe. Do you think that for a given task, it's relatively easy to know what the prior would be? Or do you think that that's actually reducing, the space of solutions that we can find, and maybe we're missing the correct solution?
I think that's a really great question, and I think it's a similar problem that you have in clustering when you kind of want to find the ideal cluster size. And so what I think would be a good approach here, if you say you have like an interacting system for which you like a really complex interacting system for which there would be many possible explanations of what would the underlying edges be, then what you could still do is you could vary the sparsity parameter, and at some point you get like a certain kink in your curve in terms of how good it is at predicting the future dynamics. And then I would just choose the smallest still feasible parameter for sparsity that gives you still adequate reconstructions before the model collapses. And that's probably the sparsest graph you have that still explains the system, and that's probably the most interesting one.
Okay, thanks. That makes sense. We can go to our next question from Geotish. Given that slot attention is good for explainability, is there work which looks at describing the slots?
That's a great question. So describing the slots in terms of extracting, say, semantic properties out of the slots. Let's say you train this model on an image in an unsupervised way, and then you would want to see if like those slots actually encode something useful about the semantic content of the scene. Maybe whoever asked the question can mention if I understood that correctly. If not, then I'm just going to assume that this is the case. Then in this case, so I think what we've seen so far, so I think this is not part of the paper, but it's pretty, if you just train a linear probe, and this has also been done in earlier work that has similar kind of architectures, is that these slot representations also encode usually all kinds of properties about the object, like its shape, its color. Color is very easy. Shape is a bit more complicated, and also its material. What's difficult is kind of getting more abstract properties out of it, like its weight or its bounciness if you have kind of a video data set. So these things might be much harder to infer.
Okay, I think in line with that question, I was just wondering, so I know that Geotish works with, he's not anymore in the Zoom, but I know that he works with biomedical data. You know how important interpretability is. So then what came to mind is, okay, when we have the slots, it's pretty easy to see what, in a way, what they mean or what they're encoding, because each one segments one single object. So would that kind of like that same approach could be used for biomedical applications in some sense, you know, having some architectures that we could, in a way, go back and easily just see what parts of the, maybe the model do, you know, what do they look at for certain predictions?
So I think these types of models are, or like this whole idea of abstracting into kind of abstract slots and learning also its binding to the input and being able to visualize that kind of binding, like what is the responsible part of the input that the slot explains. That can be used, I think, across different domains. It's just the question of how can we train this effectively. Like if you have biomedical images with very complex textures, I'm pretty sure this model, if you trained it as a pure autoencoder, would likely fail. So you would kind of need some other inductive biases. At the same time, the data doesn't even have to be an image. So the same kind of property what I mentioned here applies to graph data sets. Like if you want to abstract a graph data set in kind of a set of abstract representations, a similar mechanism could be applied. And I mean, like things like differentiable graph pooling have a very similar kind of formulation than what we presented here.
Yeah, yes, that makes sense. Perhaps we could have a final question. So any ideas how to get rid of the limitation of having to choose the number of slots in advance?
Yeah, that one's a really great question. And I've seen recently some work exploring this in terms of other stochastic processes. So you have like, so in this case here, what we've done is we inspire the model by a regular clustering method. And we make this clustering method differentiable and just more efficient at training. There are also like clustering objectives that allow you to control for the number of clusters. And that basically the algorithm infers the optimal number of clusters at runtime. And these can also be integrated with these models. So I've recently seen a follow-up paper to GNNS. GNNS is one of these models that does like unsupervised object discovery. I forgot the name, might have been called GNNS v2. So if you Google for that, I might find it and put it in the Slack channel. But that effectively proposes a way of getting rid of the predefined number of clusters. Okay,
that sounds very good. So we have to end here. Thank you so much again for the amazing talk and for your great answers to our questions.
Yeah, thanks so much for having